The next talk is also by Matthew Brennan on universality of computational lower bounds for submatrix detection.
So I'm back. And this is joint work, again, with my advisor, Guy Bresler, and with Wasim Halehel. And so this talk will be on universality of lower bounds, and also based on the Planet-Clique conjecture. So first, let's consider two problems. Biclustering and the detection of a single hidden community in sparse graphs. So biclustering is, again, a detection problem where under the null hypothesis, you observe a matrix of IID Gaussians, centered Gaussians, and under H1, you observe the same matrix, but now with an elevated mean along a k by k principal submatrix. Now, this model's been studied extensively, and its information theoretic limits and computational barriers have been characterized, also characterized based on the Planet-Clique conjecture. And the community detection problem, in the community detection problem, you observe an n-vertex graph G, and the task is to decide whether or not it's been sampled from a sparse Erdős-Rényi random graph. Here, think of Q as tending to 0 rather quickly, like polynomially in n, or if it's been sampled from this graph with a k-vertex subgraph planted with twice the edge density in the rest of the graph. And again, it's been very well studied and characterized. So in particular, papers by Ma Wu, Hayek-Wu Xu, and our Colt paper last year characterize that the Planet-Clique conjecture implies that the computational barriers listed here are exactly the computational limits. We have both corresponding upper bounds and lower bounds. So if we plot if we divide the parameter space into three regions, the regions in which the problem is information theoretically impossible, PC hard, and can be solved in polynomial time, we arrive at suspiciously similar plots, like identical plots. And here the x-axis is the sparsity k plotted on a log scale, and the y-axis is 1 over the signal, also plotted on a log scale. So this raises a general question, like how universal is this statistical computational gap, and more in particular the phase diagram I just showed you. So both of these problems are very closely connected to the general submatrix detection problem, in which you observe a matrix M, which is n by n, and the task is to decide whether or not it's pure noise, so its entries are IID sampled from some distribution Q, or if it's that same distribution with a planted principal k by k submatrix of IID samples from another distribution P. So the question we seek to answer in this talk is for what distributions P and Q, like generally over some measure space, can we characterize the statistical computational gap through average case reductions from the Planet-Clique conjecture? So there's been a plethora of work on universality of information theoretic limits and of algorithmic guarantees. But to the best of our knowledge, this is the first universality principle for computational lower bounds. And one remark I'll make is there's something surprising which emerges from the reductions in this work, which is that in general, the difficulty of average case reductions is mapping to a particular distribution. That's usually what the technical difficulty arises out of. And here we have to sort of do this in a strong sense. We have to map simultaneously to many, many different distributions in order to obtain a universality principle. And somehow this ends up being almost technically easier than in the information theoretic case, which is somewhat surprising. So first, before we proceed to state the results, we need to identify some assumptions on P and Q. So the goal is to identify a statistical computational gap in the general submatrix detection problem as a trade-off between NK and some notion of signal between the two distributions P and Q. So what is the right notion of signal? Well, it should be something like how easy is the classical binary hypothesis testing problem between P and Q. So consider the classical setup. Neiman-Pearson tells us that the optimal test is thresholding the log likelihood ratio. And a classic analysis with turn-off bounds shows that the type 1 plus 2 error of this test is upper bounded by e to the minus m e sub p tau plus e to the minus m e sub q tau, where tau is the threshold in the log likelihood ratio test. And e sub q here is a standard Chernoff exponent. So it's the Legendre transform of the log likelihood ratio between P and Q. So just to summarize the previous slide, a pair P, we'll define a pair P and Q to be computable if it satisfies a few simplifying assumptions. So P and Q are mutually absolutely continuous. They have finite KL divergences. There is an oracle that outputs a sample from Q in polynomial time. And there's an oracle computing the likelihood ratio between P and Q in polynomial time. This is necessary for like information theoretic upper bounds and algorithmic upper bounds. And to summarize what we thought from the binary hypothesis testing setup, the measure of signal that we'll have is the symmetric KL divergence between P and Q, and also these Chernoff exponents. Because you can think of the symmetric KL divergence as some notion of the signal, and then E sub P and E sub Q are just notions of concentration around the signal. In particular, lower bounds on E sub P or E sub Q correspond to large deviation principles for the log likelihood ratio. Okay, so now we're in a situation where we can state our main computational lower bound. Suppose P and Q is a computable pair, and the KL divergence between P and Q is much smaller than n squared over k to the fourth if k is larger than root n, and we have a large deviation principle, in other words, a lower bound on E sub P. Or we're in the low sparsity regime where k is much smaller than root n, and the KL is just basically below a constant. Here, little p denotes the density in the Planck-Lie conjecture. And we also, once again, have a large deviation principle. Then the Planck-Lie conjecture implies that at edge density P, the PC conjecture implies there's no polynomial time algorithm solving the general submatrix detection problem. So that is a bit of a mouthful of a theorem, and we're going to simplify it in the case where we have something weaker than a sub-Gaussianity assumption on the log likelihood ratio. So here are some technical conditions which are on P and Q, and under these technical conditions, which are actually much broader than they appear. They're all weaker than sub-Gaussianity of the LLR. We recover the same diagram as from biclustering and for single community detection. So here I'll just give a brief sketch of how the reduction works. So we begin with a Planck-Lie instance, and then we embed it as a principal minor in a slightly larger matrix, and plant diagonal entries. One technical remark I'll make is that even though they seem somewhat trivial, getting these diagonal entries and then asymmetrizing ends up being a fairly important technical obstacle for these reductions. Like previous work for biclustering and community detection, the main analysis went into analyzing the repercussions of these diagonals as you pass them through their reductions. So once we perform that gadget, now we apply something called, that we term multivariate rejection kernels, which are just a rejection sampling based technique for sampling these product distributions. And the idea is that we can construct a simple map based on rejection sampling that sends ones to L by L submatrices of IID samples from P, and Bernoulli P to the same for Q. And as a result, we end up with the matrix we want, and we've now dilated it by a factor of L. And it turns out that that exactly the loss in KL that you get from applying these MRKs ends up trading off exactly with the increase in sparsity and the increase in dimension from L in a tight way. And thank you. That's it. So it does not. So that actually is the perfect example actually for this talk, because that's an example of P and Q that doesn't fall under this phase diagram. It falls under the problem of general submatrix detection, but like you're talking about the log density threshold. Yeah, so that yields a different diagram. And so having a universality class that captures that would also be like an interesting open problem.